Alright, let's start this insurance assignment so that I can go to bed. Okay, so how do you determine the number of primes that must be tested in order to determine if a polynomial is prime? Okay, so if we remember what we talked about in class, if you have factors of a number, obviously you have a smaller factor, and then you have a number that you would multiply that smaller factor by, which would be the larger factor that would turn it into the composite number. So basically you have to find the halfway point of the possible factors. So to find that possible halfway point, we would take the square root of the number we're trying to determine whether or not it is prime. So let's start with, for an example, 327. I take the square root of 327, I get 18.08. That means I have to test all of the primes that are to the left or less than 18.08. And obviously if there was a prime number to the left of it that would multiply to be 327, there would be a number to the right of 18.8 that would be its essential pair, that when I multiplied those two numbers together it would turn into 327. So I listed the primes that you would have to test: 17, 13, 11, 7, 5, 3, and 2. And as you test these primes, you would divide 327 by those prime numbers, and once you get down to 3, you realize that 3 does evenly divide 327, so 327 is not prime. The next question is, how can you determine the remainder when a polynomial f of x is divided by x minus c? So the remainder theorem is a nice fast way of determining whether or not a polynomial has a remainder. So you do not have to go through the division. You can use the remainder theorem as long as the degree, as long as you're dividing by x minus c or x plus c. You can put whatever the value of c is into the polynomial to determine what the remainder is. So if you know what the polynomial is, you can just substitute c into the polynomial to determine what the remainder is. You want to be careful though, because if it's x plus c, if I'm dividing by x plus c, obviously you would put p of negative c, or you'd put negative c into the polynomial to determine what the remainder is. Alright, so the next problem is, how do you convert between base 10 and base 2? You may be asked to go from base 2 back to base 10, but the process is still the same. So just a reminder of why we have these different bases. 352 can be written as a polynomial. It can be written as 3 times 10 squared plus 5 times 10 to the first plus 2 times 10 to the 0 power. And so essentially, I have these. What if I were to change, this is why we call it the base. What if I were to change the base of this power? We consider this to be a power. It's got a base and it has an exponent. If I changed the base of this power, and what if I could write a polynomial where the base was, instead of 10, it was 2. So essentially I'd have these coefficients a, b, all the way down to d. I just used variables there. Whereas instead of having a 10 there, what if I was multiplying by 2? So the first thing you need to determine is how many, well, I really shouldn't say how many, but what is the highest power of 2 in 352? So 2 to the 8th is the highest power of 2 in 352. 2 to the 8th is 356. So when I subtract 256 from 352, I get 96. 96 is what I have left to work with. So then I have to think to myself, what's the highest power of 2 in 96? Is there a 2 to the 7th in 96? Well, 2 to the 7th is 128, so no. So there are no 2 to the 7ths in this polynomial. But there is a 2 to the 6th. 2 to the 6th is 64. So we take 96 minus 64 and we get 32. And so now 32 is actually 2 to the 5th. So I would take 1 2 to the 5th And if I subtract 32, you can see that I have nothing left to work with. So that's why I have zeros in all of these places. And if I were to write this as a polynomial, it would be 2 to the 6th plus 2 to the 5th, or excuse me, 2 to the 8th plus 2 to the 6th plus 2 to the 5th, and then that would be it. And I could type that into my calculator or do it by hand and see that that would equal 352. Okay, the next topic, prime factorization of an integer. So essentially, if we're looking for the prime factorization of an integer, you can build these factor trees. You break it down until it's just the set of prime numbers whose product would end up being the composite number. So if I were to take 360, for example, and break it down into its primes, I would have 3 factors of 2, I would have 2 factors of 3, and then 1 factor of 5. If I multiply those together, I get 360. So that's essentially what a prime integer is. That shouldn't be anything too tough, but a prime polynomial is a little bit more challenging. So a prime polynomial is essentially one that can be broken down into its factors. You can see I have this polynomial here that I have factored, and I've gotten it down to 4 times the quantity x squared minus 9 times the quantity x squared minus 5. So now what I'm doing is taking the x squared minus 9, and I'm saying, okay, are there any real zeros of that polynomial? So could I take that x squared minus 9 and find real zeros of it? And yes, I can. I can find x minus 3 and I can find x plus 3. Both of those have, those would be the 2 real zeros of x squared minus 9. The same with this x squared minus 5. I could find real zeros if I used the quadratic formula, or if I just knew a little bit about factoring, I could factor that into x minus the square root of 5 and x plus the square root of 5. Now, we're not really used to doing this, but essentially what I want you to understand is that both of these are real numbers. The square root of 5 and the negative square root of 5 are real numbers that I would be able to substitute in for x so that I would get zeros out so that they would end up, so the polynomial would end up being 0. But what if I have a polynomial like x squared plus 1? What if x squared plus 1 was one of these factors? Well, this cannot be factored over the real numbers. If I were to factor it, I would get this, x plus I and x minus I, and both of those are complex zeros, meaning they have a real part and an imaginary part. So if I were to leave, this would stay as x squared plus 1. So I would keep that. Let's say that instead of this x squared minus 9, it was x squared plus 1. I would leave it like that because I can't factor it any further over the real numbers. So we talked about how polynomials have an expanded form and they have a factored form. Once you've factored a polynomial down to where you cannot factor it anymore over the real numbers, that is when it is a prime polynomial. So there's not really much on the test about this, so if you're a little bit confused by it, don't worry about it. There's really very little on the test about it anyway. But it is somewhat important, and I think a little interesting as well. So I wanted to include that in the insurance assignment. Okay, so how can you determine if the degree of a polynomial or the degree of a polynomial by looking at its graph? Essentially, you just count how many turning points it has and add 1 to it. So in this case, this polynomial has a turning point here, a turning point there, and another turning point there. So there's 3 turning points, add 1, and I get a degree of 4 for that polynomial. The next one, what does it mean for two numbers to be in the same congruence class for a modulus? Okay. Okay, so if two numbers are in the same congruence class, so for example, if A is congruent to B mod M, that means that essentially A and B have the same remainder when they're being divided by M. One of the ways that you can check this is by taking A minus B. If I take A minus B and then I look at what A minus B is, M should be a factor of whatever A minus B is. So for example, 11 is congruent to 1 mod 5. 11 minus 1 is 10, and 5 is a factor of 10. Another way of looking at it is, if I were to write 11 as 5 times a number plus a remainder, I would write it as 5 times 2 plus 1. If I were to write 1 as 5 times a number plus a remainder, I would write it as 5 times 0 plus 1. And we can see that both of these, both 11 and 1, have the same remainder. So they are in the same congruence class because they have the same remainder for that modulus. Okay, and the last one, how can we determine if a 0 has a multiplicity? I gave you an example here of one way you can try to look at a graph to determine where a multiplicity may occur. So here at A, which we would assume to be a negative number based on where the origin is here, this doesn't appear to have a bend in the graph at all. It looks like a straight line going through A. So if I had to make an assumption, I would say the degree of that 0 is 1. So there wouldn't be a multiplicity at that 0. However, at B, we can see the graph come down, hit B, and then go back up. So if I were to make a guess as to what the multiplicity might be at B, I might say that it's 2. The multiplicity is 2, and really I would be safe to say that it would be it could possibly be 4, it could be possibly 6. Any even number multiplicity would have that bend to it as we come down, touch B, and then go back up. And then at C, you can see that the graph bends. It almost looks like a cubic function. It bends, it hits C, and then continues in the negative direction. So we could say that maybe it's a cubic function, but I can definitely see there is a multiplicity there because of that bending that it does at that 0. So I might say that that has a multiplicity of 3. So essentially you just have to look at the graph and say, okay, yeah, I can see there's a parabola type thing going on here. So I can say that there's a multiplicity at that 0. I can see this bend here. Maybe there's a cubic or definitely an odd numbered multiplicity going on at that 0. So that's pretty much it. This one was a short one, so hopefully you guys appreciated that and didn't have to go through an hour's worth of me talking. Alright, have a good night, and I will see you guys for your test on Friday.